Hi everyone, my name is Shadab. I'm faculty at Department of Theoretical Physics, Tata Institute of Fundamental Research, Mumbai, India. Today I'm going to talk about Beyond the Cosmic Backdrop, accounting for environmental effects on galaxy and quasar evolution. I'd like to start by thanking the organizer for Cosmology at Home for giving me this opportunity to discuss this topic, which I've been working on for some time. Okay, so let's get started. The first thing I'd like to start by saying that if you had to go and see the night sky with a telescope, let's say a 4 meter class telescope, what you're going to see is an image of something like that. This is a composite image from Legacy Imaging Survey in 3 photometric band, and that compared to the size of the moon. And what you see is really small blobs as a galaxies. And if you want to understand more detail about these galaxies, what you have to do is you have to follow up with more detailed experiments, something like spectroscopic observations, so that you have the galaxy SEDs, and then you can distinguish between different kind of galaxy and their different properties. So broadly speaking, we like to think about in large scale structure surveys about roughly three kind of galaxy, although it's a continuum. One of them is called red galaxy or luminous red galaxies. These are old galaxies which doesn't have much star formation going on. The other is what we call blue galaxy, or sometimes we also call emission line galaxy for a particular context, which have active star formation going on. And then there are galaxies which have active black holes at the center. These are supermassive black holes, which are causing one of the main activity and the emission from these galaxies. And these things can be identified and looked at by looking at their spectra once you have observed them spectroscopically. And once you have the spectra, you could also try to get a sense of what sort of overall environment these galaxies are living in by estimating densities of galaxy at the location of various location. And so the bottom map is a follow-up of the same part of the sky with a small fraction of galaxies spectroscopically identified in these three categories, and then an estimate of what the dark matter distribution would be in these regions by essentially relating galaxy density to the dark matter density. Now, if you want to go ahead and think about a larger scale, what you're going to see is a large scale structure if you zoom out from the image I showed you. And so you see a cosmic web and this intricate structure, which is traced by galaxies themselves. It's also traced by dark matter, which is inherently tracing the structure. And at these scales is where you get information about cosmology. So if you are interested in cosmological constraint understanding and asking questions with regards to cosmology, then you have to look at these very large scales where it's determined by cosmology itself. And so you can look at these things at various scales, and then the different physics which is going to operate and dominate is going to be different, which is what this talk is about, which is what you need to be careful about. So if you want to sort of look at what is the current understanding of how these things happens, is that the universe started with the initial condition. We have fairly good understanding of how the initial condition of the universe was. There is still some open questions, and people are still trying to work on that. And Galaxy Survey is part of that effort. But once you evolve that initial condition based on our best understanding of the model, let's say lambda CDM with GR, what you see is that intricate structure forms, and we see this very intricate thing, what we call cosmic web. In this cosmic web, we'll basically have the overall dark matter density fluctuation, which has grown, and then gravitationally collapse to form this collapse region, what we call dark matter halo. For example, some of them are very massive, one are labeled here. And this dark matter halo provides the interesting environment which will have necessary and sufficient condition to have further collapse and form things like stellar activities, and hence galaxies and different kind of galaxies and things like that. And so our sort of primary picture is that is the dark matter halo where all sort of playground for all kind of galaxy formation activities. And we are trying to expand from that and see beyond dark matter halo what else affects these things. Okay. Now, if you think about that picture, what you also want to think about is that there are different scales, right? So if you look at very large scale, like 100 megaparsec over H, then that's mostly dominated by the cosmology itself, like how the structure at very large scale evolved in the universe. And when you go down to smaller and smaller scales, at some point, what you'll see is that the linearized version of our models start to fail when, and it fails very strongly when what we call shell crossing happen, which is to do with the halo formation itself. And so there are scales where halo formation effects start into play, and this is what we call already nonlinear scale or nonlinear matter power spectrum regime. And then if you go even further, then you will get to the roughly the scales at which galaxies form, and you'll be more sensitive to the physics of galaxy formation itself. The galaxy itself is about 0.1 megaparsec over H kind of scale. There might be some transition where one halo versus galaxy, one of the physics is more dominant, and we are not sure where that scales looks like. So when you look at the things I'm going to talk about, keep in mind that the different scales are involved, and all of these physics are probably important at a large range of scale, but then there are regime where one is dominant over other, and so you might want to keep asking about that aspect. Right. So one of the question we want to address is that, let's say if you were to do a survey of galaxy and you look at some specific kind of galaxy because of our constraint with observation, then are we sampling the cosmic wave fairly? And if we are, on whatever sampling we are doing, can we learn from that about the physics which is operating and regulating the evolution and formation of galaxies themselves? And will this matter if we are trying to use these galaxies to make a statement about cosmology, so cosmological interpretation, right? And so I want to talk about one specific way to characterize the environment, because that will be useful for later part of the talk before I talk say why it is important. And so one of the way we characterize the environment is essentially what we call tidal overdensity and tidal field. And so just very briefly, let's say if you have a survey covering some part of the sky, you're going to make grids of certain size. And the size of the grid itself is a difficult question to answer. But once you have that grid, you can estimate density as a function of position in your survey. So rho of G, galaxy density, as a function of XYZ. You can convert to a more interesting quantity for, especially from the cosmology context, it's called overdensity, which is essentially density over mean density minus one as a function of position again. And then you can do Fourier transform and go into Fourier space of the density. So that's delta GK. That can be related to what we call tidal tensor. Essentially, if you write the Poisson equation, then you can show that the derivative of potential, second derivative of potential, which is important when you think about the tidal field, in Fourier space is basically just given by the factors of K and the overdensity in Fourier space. And so that's why we are interested in that. And then you can do another Fourier transform to look at the tidal tensor in real space, which is essentially second derivative of potential in this 3x3 matrix. And once you write down the matrix, you can sort of figure out what are their eigenvalues. And using these eigenvalues, this is essentially traces how the tidal field is in different coordinate axes or along different eigenvectors. By looking at these eigenvalues, you can define quantities which will sort of quantify the tidal field around each of these locations. And so we define one quantity which we call tidal shear, which is basically the differences of these eigenvalues. And then we define another quantity called tidal anisotropy, which is essentially tidal shear divided by 1 plus over density. And I'll show you why we do that, which is a recent interest and recent lots of interesting physical insight why that is valuable. So if you look at the tidal anisotropy, this is for a simulation and plot it as a function of overdensity, which is the first quantity I defined at some scale. Then what you'll find is that the tidal shear is actually quite correlated with overdensity. And this is not ideal if you want to sort of look at the two different things and separate them. If they are highly correlated, it makes everything much more harder to interpret. And so to avoid this reason, and you can reason it out from the, at least in the linear theory, why this needs to be the case. We have defined a quantity called tidal anisotropy, which is essentially scaling out by the overdensity, your tidal shear. And then you find that the tidal anisotropy and overdensity is much less correlated. They are basically both are independent tracers of the environment. And that simplifies all the further analysis we are going to do. This was first proposed by Asim Pranjbe and his collaborator not that long ago. And there is a series of paper on the quantity tidal anisotropy. If you're interested, it's a very interesting quantity, how that helps you understand the tidal environment better and the fundamental nature of that. So now that you have a context that there are different scales, and we might be looking at different kind of galaxies, and you want to sort of understand that how these galaxies are sampling different environment, to then think about, okay, how that can affect cosmology interpretation, but also to think about, okay, how can I learn about galaxy formation models, or how can I improve my subgrid physics in a galaxy formation simulation, hierarchical simulation, governed by the data. Then one of the things you'd want to do is that you want to see what kind of things you're seeing in the data, and that can be a guiding principle. And so I wanted to show you a few examples of where we have seen evidence of environmental effect on galaxy properties, to give you some flavor of what kind of things have been already seen, and then some indication of how that affects cosmology, how that connects to cosmology. So one example is that if you look at galaxies, let's say if you take a survey called epochs, if you're not familiar with that, please, epochs survey is very well explained on their web pages. But essentially it's a cosmology survey which looked at different kind of galaxy, and so it's targeted two different kind of galaxy, red and blue galaxies, or luminous red galaxy and emission line galaxies. And if you look at that sample of galaxy and sort of divide these galaxies as a function of overdensity and tidal anisotropy environment on the two axes, and look at, okay, how many galaxies are red? What is the fraction of red galaxy as a function of these environment? Then this is what we found on the data. And so what we see is that low density and tidally isotropic environment, which will be equivalent to voids, have a much smaller fraction of red galaxy compared to high density filaments. And also high density tidally isotropic region like clusters also have a larger fraction of red galaxy. And interestingly, low density filaments, so low density but tidally anisotropic regions, also have significantly larger fraction of red galaxy compared to low density tidally isotropic environment. And so this is interesting, and for the first time we have seen this. But then what you would want to ask is that, how much of it has to do with anything of their galaxy, let's say color or star formation rate is governed by certain aspect of tidal environment versus how much is just the fact that these galaxies are living in different halo masses, they have different linear bias, they have different mean host halo mass. And so you can write on a very simple model where you say, okay, you think these galaxies only care about their host halo mass and doesn't care anything about the environment, and see what your red fraction looks like. And so we did that exercise where in the simulated galaxy, it reproduces the 2-point function of these galaxies observed in epochs data, but doesn't have any environmental dependence. And so what you find here in this case is that overall, in terms of the overdensity relation, on an average, the data reproduce it because overdensity is also tightly connected to the host halo mass distribution. But on the tidal axis, especially in the low overdensity environment, in the environment where the overdensity is small enough that the halo can have more significant role in terms of what happens, we find that this model do not predict what is seen in the data, particularly in low density, tidally anisotropic environment filament. There's significantly more significantly more blue galaxy in the simulation compared to data. And this is a statement that the kind, if you think that it's just the host halo mass, in the host halo mass distribution here is very different from what you'd see in the data. So that's the first example I wanted to show, that there are now hints that these kind of effects are pretty significant in very large survey, which was which was not that clear in the earlier survey. And so thinking about, okay, what kind of additional environment these galaxies must care about in their color to reproduce this is an interesting exercise which we are still trying to do. Now, another example of how these galaxies care about more than just the host halo mass of the halo they are living in is what we call conformity. And so by conformity, what I mean is that particularly one halo conformity is that if there is a dark matter halo and in which there are several galaxies, some of them are red, some of them are blue, then will that matter the fraction of blue galaxy in this halo? Will this care about what is the central galaxy and hence overall environment of this halo? And so what it might happen is that if the central galaxy is red, then the more fraction of the satellite galaxy is red rather than blue. And that's a hint that there's a galaxy formation effect called quenching, which is an operation. And if the central galaxy is red, then more likely it's in an environment where more of the satellites are quenched. And so this is what we call one halo conformity. So again, looking at the epochs data, and if we look at the galaxy clustering, something like 2-point predicted correlation function for luminous red galaxy, autocorrelation, emission line galaxy autocorrelation, and their cross correlation, what you find is that if you do not put any kind of conformity, then your model, which is shown in the red line, overpredict the cross correlation at scales of few megaparsec. And if you put in this additional correlation that these things are conforming to the central galaxies, then you produce the green line, which is more consistent with data. And there's about between 2 to 3 sigma detection about one halo conformity in this signal. And so that's another example that, if you're targeting only red galaxy or blue galaxy, they are preferentially living in certain kind of halo beyond just what the total mean bias fair sampling of the cosmic wave would look like. Right. Now, I would like to move on to a third example of galaxies on the occupation itself. And so this is basically making a statement about what is the probability of having a certain kind of galaxy given the host halo mass. Can that have some more interesting environmental effect? So before I go into this example, let me just show you this very simple plot from simulation, which is showing the distribution of halo mass as a function of mass of the halo, and again, tidal anisotropy, the quantity I already described in the simulation. And what you find is that in the massive end, when the halos are very massive, they essentially control their environment, and they're mostly in tidally isotropic environment because they're dominant thing. Everything else is subdominant, right? But as you go to lower and lower mass, the distribution of tidal anisotropy or tidally halos living in more and more tidally anisotropic environment, because their environment is determined by other things around them rather than the halo itself. And so as you go to the lower mass, this is much wider distribution. Now, if you think about this galaxy surveys, the previous generation surveys, such as, Slow Indigo Sky Survey, the luminous red galaxy is living roughly mean halo mass of around 10 to the 13, right? So it's really in the regime where the distribution is not so wide. Now, if you look at surveys like DESI and LSST and Euclid, they will easily go and sample galaxies drawn at 10 to the 12 and 10 to the 11 halos, right? So host halo mass of 10 to the 11 and a few times 10 to the 11 and 10 to the 12. And so now they will be actually sampling galaxies in much more diverse tidal environment than before. And so this question becomes even more important, that how important is the tidal environment and how are we sampling that? So given that context, you might want to think about two things. One is in simple HOD model, if you're familiar with that, you're basically asking, given a halo, given its mass, what is the probability to have a central galaxy? And so this is what is shown here. What is the probability of central galaxy as a function of host halo mass? And the x-axis is again tidal anisotropy. But my model do not have any freedom to correlate with tidal anisotropy. So by default, this will always be only a function of halo mass. The model do not have any freedom, although I'm plotting it as a function of tidal anisotropy. Also, for each halo, you can have number of satellite galaxies. And so how many satellite galaxies you're going to have for this sample is a function of host halo mass only and doesn't depend on the tidal anisotropy. So this is for, as you can see, in this sample, this is for gamma survey, we already are populating at 10 to the 11 or 11.5 halos at some non-zero significant probability. Now, if you want to look at beyond halo mass, often 2-point function is not enough. And so that's what it was used to make this analysis. So you might want to include something beyond 2-point function. And so one of the quantity which we have written about is called Voronoi volume function. So what this is that, let's say if you have a discrete tracers as galaxies tracing the cosmic web, you can essentially tessellate the field around these galaxies using Voronoi tessellation scheme and calculate the volume of each of these cells. And then you can look at the distribution of this volume itself. And this is what we call Voronoi volume function, the distribution of volume itself around these galaxies. And so if we include that, then what you see is that the model is constrained again with slight different dependence. But again, we do not have any freedom to couple with the tidal environment. But let's say if we do allow a freedom to couple with tidal environment, what you see is that we introduce two additional parameters and we say now the occupation number or occupation probability is a function of tidal environment also for both central and satellite. And you start to see that this is no more a flat curve like in these example. So now you start to see a slope, but the slope is not that significant in this case, and also for satellites. But it's also reasonably significant. And let's say if you include both VVF and 2-point function and allow this freedom, then your final result looks like you have significant slope in occupation probability for central galaxy as a function of halo mass and tidal anisotropy. It basically means that if you take a sample like this, like gamma magnitude limited sample, then you're going to find that the occupation probability for central galaxy should be a function of tidal environment as well, and that will give you interesting characteristic in terms of the final sample you're going to look at, and it will show impact on all the statistics you're going to measure for both central and satellite galaxy. And in a nutshell, what this is showing is that when you go to more tidally anisotropic environment, then the probability of occupying a central galaxy for even a smaller halo mass is larger compared to a lower halo mass case, right? And then similarly, if you look at the satellite galaxy in an anisotropic environment, there's a fewer number of satellite galaxy at some fixed halo mass compared to an entirely isotropic environment. So this is what these two slopes means. Now, let me try to put this in a little bit more visual context so that you can have a bit more connection. This is the example of a simulation where you have galaxies populated as central galaxy shown in circle with the color indicated by the halo mass, as well as the size indicated by halo mass, and the satellite galaxies are shown as a star. And this is we used a model which matches gamma, but it doesn't have any environmental dependence. It's a host halo mass only case, which means, let's say if I'm going to say that my HOD parameter is dependent on additional freedom alpha central and alpha satellite for both central and satellite galaxy, then I set it to 0. Essentially, no environmental dependence is there. Then you see a picture like this. Now, let's see if I show you just for the context example where I set these parameters to be large value, then how will this picture look like? So this is a toy example where I've set alpha central equals to -10. It's the same direction of the slope we saw, but it's much stronger slope, much stronger tidal anisotropic dependence. What you see is that all this tidal isotropic region, basically there's no central galaxy anymore, because these were all low halo mass which are populated, and by introducing this dependence, I've said that they cannot host any central galaxy anymore. And you see much more stronger filamentary structures because these are the environment which is tidally anisotropic, and they have higher probability to host host central galaxy even at lower halo mass compared to isotropic. So this is the kind of difference you're going to see in the two universe. And if I show you the example for what our best fit looks like, then this is much more milder compared to what you saw in the original figure. And you see that again, the void region is slightly emptier than the original picture where we didn't put any tidal environment correlation. And so these are the values of the parameter, and then overall it's about 3 sigma detection of occupation of tidal environment, correlation of tidal environment and occupation number of central and satellite galaxies for low redshift sample, for deep sample. Now, so you have seen several examples of signal detected in observations indicating galaxy halo connection more complex than vanilla. So now we are seeing this in the data, and we have also have some handle on how strong it is, because one of the complexities is that if you don't know the strength of the signal, you can, and if you make the signals too strong, then you'll always see that the cosmology is going to be very sensitive. And so it's also important to have a sense of how strong these signals are. Now, let us talk about how do they connect to cosmology part of it. So that's what my rest of the talk is going to be. And so typically, the picture I want you to keep in mind is that we do galaxy survey, we calculate summary statistics, we look for sometimes features like baryon acoustic oscillation, distortions, and then from there we interpret cosmology. So this is the context we are looking at this kind of thing. So first of all, galaxy statistics, I've already used this, but just for completeness, I wanted to quickly say, when you think about two-point function, it's basically talking about what is the excess probability of finding a pair of galaxy at certain distance compared to a uniform random distribution. So you can go to your survey and sit on each of these galaxies, draw these rings and count how many galaxies you have, and then do that as a function of radius and average over all the galaxies. That's the number of pair of galaxies. Repeat that exercise with a random distribution, take the ratio and take -1. This is what 2-point function is going to look like. So this is the measurement of 2-point function. You can see it's basically decreasing with distances, which is what you expect in a lambda CDM universe. And there's an interesting feature here about 100 megaparsec, which you cannot see directly, but if I zoom in, then this is the feature, which is what we call baryon acoustic oscillation BEO. It's a remnant of sound wave physics in the early universe. And you can also do this exercise in the Fourier conjugate space, and that will be essentially what we call power spectrum, doing the Fourier transform of the density field and then correlating the Fourier transform version of the density field. To show you an example, this is a BO measurement from the epochs survey, where I have now scaled the y-axis by s squared. And you can see there is very clear detection of BO peak at about 100 megaparsec over h. And this is roughly 2% measurement of BEO. You can treat this as a standard ruler and constrain a lot of cosmological information. In fact, this is one of the most successful cosmological probe after CMB, and it is going to be something, one of the core thing for many of the upcoming surveys. So now, how does baryon acoustic oscillation is connected to all the galaxy physics we have looked at? So note that baryon acoustic oscillation known as a very robust tracer. And so in that context, I'd like to show you this one slide on this topic, that if, let's say, if you were to do this exercise of simulating various kind of galaxy sample, keeping the number density and linear bias same. So basically all of these things will match the same 2-point function, and look at for these BO peak and do a very precise measurement. But the difference is that each of these models are looking at different distribution of the host halo mass. So they don't have exactly the same distribution, although the mean host halo mass will be the same because you're fixing the bias. And so there are many different kind of models here. And if you do the entire BO analysis, this is what you'll find about the BO scale, the difference of BO scale compared to the true value, which is shown with the black dashed line. And what you see is that all these stars are the scatter in the BO scale, and this is roughly at 0.2% level. So you see a 0.2% scatter in BO purely coming from the fact that we don't understand in detail what is the host halo mass distributions of these galaxies. Now, if you include the environmental effects, sensitivity to environment, let's say I create models which have various environment, which is guided by the things I showed you in terms of the strength of the effects as well as what kind of effects are seen in the data, then what you see is, again, you get a scatter of roughly 0.2%. So you get about 0.2% error based on these tests, and you can improve this because this is also limited by how precise our simulations are. So if you say that, okay, you cannot do better than that, then you cannot measure BO better than 0.2%. And when you measure BO at 0.2% precision, that means you are at your systematic error and the statistical error are equal. And so you don't want to be in that regime. Now, if you look at the recent paper from DESI collaboration, if you look at the baryon acoustic oscillation for galaxies and quasar, then they give their table for summary of systematics, which has basically 3 entry, and each of those entry have many different layers. But at this 3 entry, the second entry for configuration space is about this effects I showed you about how exactly galaxies are connected to the halo and their environment. And that is about 0.2% is what I told you already. But this, also note that this is actually not the dominant systematic effect compared to anything else, right, in this. And this is what determines or will set the floor for precision of BAO if this stays at the same level with the further more improved test. So although I should also note that this 0.2% is dominant effect coming from this galaxy physics sensitivity, but this is negligible compared to the current BAO precision. So BAO remain to be a very robust probe of cosmology. But as we improve the precision of BAO, this will be one of the things which is going to hit us, and we need to be careful about how to improve upon or evaluate our understanding of galaxy physics and improve the BAO precision. Now, let me quickly talk about redshift-space distortion, which is the other probe for especially spectroscopic galaxy survey. So very quickly, when we measure these galaxies, we measure their spectra, we measure redshift. The redshift have observed redshift have cosmological redshift, which is basically the what we are interested in to first order if you are interested in cosmology. But these galaxies are also moving, and so they will have peculiar velocity, which will also be added to the redshift, and then there will be terms because of gravitational potential they are living in gravitational redshift, and there will be other higher order term like Doppler effects and things like that. And so because of this peculiar velocity, what happens is that when you look at decompose the clustering signal parallel to the line of sight and perpendicular to the line of sight, it does not look isotropic. So if you are to make a plot of correlation function again, parallel to the line of sight and perpendicular to the line of sight, in place of iso contour being circle, you say this ellipse, which is essentially following this large scale infall of galaxies. And this is very well understood. And you can model it to good approximations with this very simple model, which is called Kaiser model or Kaiser formula. But unfortunately, there's more complication than that because there will be multiple galaxies living in the same halos. These galaxies will have very random motion, and that will be a very nonlinear effect. And so if you look at the full correlation function, it will look like this with this central feature, which what we call finger of God, and it's very nonlinear. So if I just isolate that finger of God and show you, then you can sort of appreciate the scales at which it's relevant. It goes up to pretty large scale, like 40 megaparsec, although this is coming from this halo scale physics. And in the perpendicular direction, it also extends to fairly large scales. And so this becomes one of the hard part in modeling redshift distortion. And this is something you want to think about. So if I want to think about the effect of galaxy physics on this, then generally I can write that the redshift space power spectrum ratio of redshift space power spectrum to the real space power spectrum is basically roughly the two term. One is the nonlinear term and one is the Kaiser formula. So let me show you a illustrative example in simulation. If I had to show you the ratio of the power spectrum, then what you're seeing is this is redshift space distortion for three different kind of galaxies. One is luminosity galaxy, one is emission line galaxy, and another is emission line galaxy. But the latter one has quenching at high halo mass, which means there are no emission line galaxy at high halo mass as a central. And so presence of these galaxy at high halo mass or not is going to make a difference. All of these have these two have same large scale bias and clustering. This one has a different. And so you can already see that they look very different, although they have exactly the same cosmology. You can look at the nonlinear term, which is essentially at large K, how this looks like, this finger of God effect. And what you see is the distribution looks actually fairly different. And so this is very interesting because now by measuring this kind of quantity, you can constrain what kind of host halos are living in, whether there are star-forming galaxy at high halo mass or not, or this quenching is suppressing, how efficient the separation of quenching is, and then you can split it by environment and look at even further detail. So this gives you a cosmological power spectrum measurement gives you access to constrain galaxy formation physics in terms of the star formation rates and things like that. Now, if you divide out this nonlinear term from that, then what you should left with is essentially the Kaiser boost, the last scale infall I talked about. And even at this level, when you do this simple division, what you see is that this Kaiser boost is not same. Because these things have same cosmology, you should expect to basically see the same Kaiser boost about modulo the factor of beta, and especially between these two. And so this is where sensitivity to cosmology is going to come in, and we have to be very careful about analyzing this. So coming back to my example that, the galaxies do care about the tidal environment in terms of their occupation probability. If you do the full exercise of, let's say, measuring omega matter and sigma 8, you compare to the Planck value and the CMB lensing value shown here. If you analyze these galaxy sample at small scales without any of these tidal anisotropy environment, you get the blue contour. And if you include the tidal anisotropy environment, then you get red contour. And so what you see, there's a significant shift, although the error bar here is large enough that this shift is not significant compared to the error bar. But these kind of shift, if we see in the current survey, then this will be clearly detected. And so it has potential to affect your cosmological information if you're analyzing redshift distortion without really modeling the kind of environmental effect you have in the kind of galaxies you're looking at. So that's another example. So after BO, which has 0.2% effect, this has much larger effect, and people are looking into this very carefully. And so lastly, I want to cover very quickly gravitational weak lensing and galaxy physics. So if you think about weak lensing, it's essentially all the structure in between the observed plane, whether it's CMB or some galaxies and us, bends the light and look at the produce correlated bending, and it's something we can look. And so there is some tension in the omega matter sigma 8 plane if you compare CMB with the weak lensing, but it's fairly weak. It's not that strong, and all of them can be consistent with the omega matter of 0.3 and sigma 8 of 0.8. But more importantly, if I were to sort of evaluate the kind of environmental effect I told you about on the weak lensing, then what is going to be the effect on weak lensing itself and hence cosmology? And so what we found here is, if you look at the red solid line and the blue cyan line, if you include the kind of environmental effect I told you, examples of those, then overall, if you look at the ratio here, the red line is basically consistent with 1, which means the overall weak lensing of the magnitude limited sample at low redshift actually not going to be sensitive to the kind of effects I showed you, where we already have signal from galaxy clustering and VVF. And so that's a good thing from the cosmology interpretation point of view, but it's not so good thing from the galaxy formation physics point of view. But if you were to split the galaxies into the central and satellites, so for example, you can look at the group galaxies versus the satellites in the group, then what we find is that the lensing strength can be very different, even at large scale. For the satellite is much more higher amplitude versus central. And so depending on how our selection is, and if we don't balance the central and satellite in our selection, then we can see bias in weak lensing as well. And so this needs to be further evaluated, and something will be interesting for the future weak lensing survey. So with that, I will leave you with my summary. There are several signature of interesting galaxy formation effects are now seen in galaxy survey. These effects has two implications. We can use these to constrain our galaxy formation physics, but these are also add additional effects on all the statistics we are going to measure. And so we need to be very careful about how we interpret cosmology using these experiments, using these kind of galaxy sample, and assess them carefully. And this is actually one of the very active topic within all large scale galaxy survey, is to disentangle such physics. It's going to be win-win for everyone interested in galaxy formation or cosmology overall. So with that, I would like to thank you for your time, and thanks a lot for listening to this talk.